importance of this presentation is the previous speakers have talked about competence, confidence, and collaboration. And Madam also spoke about reaching out, respect, and relevance. Good. So this presentation is actually going to engage you. I want to develop some programming skills among you, because before I left for Australia, I did a presentation at UMAT for, I think the geomatic guys were having a association, and I can tell you at least I had 2 guys who took it up and they did a very good project which were also programming based. So I hope today after this presentation to engage you. All the importance of this is just to engage you, for you to know there is something called linear programming. It's something which is applicable in every field. Actually, it's a field under operations research. So anyone who is into engineering, who is into manufacturing, anywhere can actually apply this. So I'll go through the introduction, a bit of lit review, just to get an understanding of what mixed integer programming is. And I'll talk about the methodology of my project. Then we will discuss the results, data analysis, and conclude. Now, the focus of this presentation is on open pit. This has also been applied in underground and even manufacturing. And as I said, this mixed integer was developed by World Bank. So most of the optimization, because World Bank, when it comes to World Bank, they do a lot of projects. And again, when it comes to, you all know IBM. IBM too is a pioneer in this programming aspect. So when you look at open pit, typical open pit, we do a lot of stripping. And when you talk about a whole open pit mine planning, if you don't know, is actually we plan the whole mine. So if you take maybe Anglo Gold, if you take Pesos, you have mining engineers who make sure the mine is profitable with the assistance of the geologists, the financial guys, the surveyors and stuff. So if you look at a typical mine planning methodology, we have what we call the strategic long term, we have the medium term and the short term. So the strategic is whereby you look at what you have, the deposit you have, then you come up with various strategic options. So based on your resources and your constraints, you come up with probably several scenarios. Then out of this, you choose maybe the one which is practicable, or the one which will give you the optimum results. Then you break it into maybe your 5-year, your 2-year plan. Then now you have what we call the short term, that is the tactical plan, because you have to execute it on the ground. So my presentation will be based on the strategic, which is the ultimate pit limit, that's where you come up with your ultimate pit limit. Then you come up with your production scheduling. Because when this side gets wrong, if this side is not well done, everything is affected. And there are various tools. So this project, the main intention of this project is, as a growing engineer, I said I want to challenge the softwares which are around. So we are using Whittle, which is the main, when you talk about, and Whittle, can you imagine, Whittle, which is being used by mining engineers, was developed by Jeff, who is a mathematician and a physicist. So he challenged himself to use that knowledge to come up with it. So being a mining engineer, I'm like, okay, let me also test what he's done. So I'm going to test it and see if I can do a better model for the mining engineer group. So we will talk about the mixed integer linear program, which is actually a growing, knowledge area for mine optimization. So the project objectives, as I said, first of all, I'm comparing. So I have to run some models with the Whittle software. Then I'll have to now develop my own mixed integer linear programming, which is actually all about linear. You see a very big word. You all did linear equations. 1x plus 2x. Do you get it? But all that you are doing is you are trying to take a problem, and then you come up with equations, then you come up with with all these equations, which area is my optimum? Which area will satisfy all the constraints that I have and will give me the optimum results? So I also do a production schedule, and in Whittle there are two methods. We have the Milawa, which is also an algorithm, MPV, and we have the Milawa balance. The Milawa MPV, what it does is it actually, when you do a schedule, all that it does, it tries to get you the best ore. So it doesn't follow the practicality of maybe having, because when you're doing a plan, normally your volumes and your fleets are constant. You can't be changing them, every year. So the Milawa MPV, what it does, it tries to just get the best ore. So normally you have a higher MPV. You all know MPV, net present value. Then the Milawa balance, what it does, I have to mine some waste and again balance my production. So that is the difference between the Milawa MPV and the Milawa balance. So I'll compare those two. Then I've also developed the model coding for a production model. Then these models, normally when you create them, depending on the equations that you build, it can run for sometimes 3-4 days. So I challenge myself that no, I'm going to use two types of equation. Sometimes you can have, we'll go through it, you can have maybe x9 minus x1, x9 minus s2, x9 minus s3. Again, you can have the same thing, 3x9 minus x1 minus s2 minus s3. So using that concept, you come up with those two concepts. So just to, you build those two models, then you see the one which is effective, and again, is it giving you the optimum net present value? Then you compare with Whittle, as I said. So the expected outcome, I actually use the GAMS. When you are doing linear programming, there are various around, but the recognized one which has, if you want to go into linear programming, is GAMS. It's more of algebraic programming language, and the C+ is the optimization engine behind it, which was developed by IBM, as I said. So that is the tools that I'm going to use. So the lit review, as I rightly said, currently most of our production schedule is, manual based. It depends on the experience of the mining engineer. And the current methods for ultimate pit limit, we have the Lich, Grossman, and the floating cone. I don't want to go so much into it. So if you look at a typical mine planning cycle, you start with your capacities, which in the linear programming language you call your constraints. So you have your processing constraint, you have your production constraint, you even have your slope. You cannot just go into a pit and start mining straight. You have to mine according to an angle. So you come up with all these, we call it geotechnical constraints, and now you feed it into your optimization software, and it comes up and tells you that of this deposit, this is how large the deposit is, this is how far you can mine to be profitable. And as I said, there are various methods. The current software that we are most mining, which is Whittle, is using what we call the heuristic. Heuristic method, which is currently used, is a method whereby you cannot really justify it. It's a mathematical programmer. It cannot tell you that, hey, this is the optimum results I'm giving you. Whilst the linear programming can actually tell you that, okay, this is the optimum, and the difference between your optimum and the normal one is maybe this percentage. And this is what we are using, because currently, if you look at the computer size that we have, our RAMs and stuff, if you are to build programming language in the linear with a very big deposit, some of our blocks are like 1 million blocks. It's very, very difficult. So it takes time, and for mining, we want everything faster. So now we are making do with this heuristic method. So we are accepting, but we don't really know that it's giving us the optimum result. So this is what I was actually saying. It's the normal linear programming is basically when you have like a graph like this, you all learned equations. So this green line is a constraint. It can be, you can mine for a whole year, you can't mine more than 2 million. For processing. Then when it comes to mining, maybe you cannot mine more than 10 million. So when these two combine, this is where you can play around with, because you can't go beyond this line. So in the linear programming tool, what we do is we try to create these equations. So you create equation for production scheduling, you create equation for processing, you create equation for your grade and all the constraints that you have within the area that you are going to mine. Then it comes out that this is the point, this is your optimum, this is what you can achieve. So that is all programming, the linear programming is all about. Components, normally in a mathematical model, you have what we call the decision variables. So the decision variables will be, how many tons do I need to mine? And you can write equations for these constraints, and it can tell you that, okay, take 10 sheds, take away. So the solution that it will give you will come up with the optimum, which will be exactly like the 23 kilograms. So that's the same principle that is being used in mine optimization. And the integer comes in because the mother of the whole thing is linear programming. When you add the integer is, if I want number of shovels, I cannot say I need 1.2 shovels. I need 1. And if I want to mine a block, it's either 1 or 0. I cannot say I'm mining 1.1 block. The same with persons. You cannot say I need 10 persons. Even when you are doing resource optimization, you can't say I need 10.1 people. You need 10, so it should be a whole number. So that's where the integer comes in. So in mining, that is why the topic is mixed integer, because when it comes to tons, it has to be that figure. When it comes to shovels, that figure. When it's block, it's either in the pit or out of the pit. So the main thing, and this algorithm, the background of the algorithm is, when you have a block model, every block model represents a value. So this block model, if you have a deposit, let's say this is your deposit from here to the down there, every block has a value, and that block has to be, valuable, profitable to mine. So what it does, it gives every block this value, and now it forms a network. So as it goes down, so it will start with this first one. Is it valuable? Then it goes to the next one. Then it adds up. So it forms a limit whereby if it goes beyond or it goes below, it's not the optimum. It's not the maximum profit that you can get. So that's the same principle that when you write the equation, that's the background engine. That is what it does. So when you fill it with a block model, it tries to tell you that this block, so it works through all the blocks in combination and comes out and tells you that this is the pit that you have to mine to be profitable. So as I said, this is the gap. So as a growing engineer, I said let's try to do something. So actually this project is a first phase. I actually want to take you to the next level, whereby you can actually sit down and put in models, and it gives you, it does the UPL production schedule, it gives you all the sensitivities and stuff. Because currently we do it in silos. We don't have a complete system for it, this is a challenge which is not Ghana, it's the whole world. That is where now most professors in mine planning are focusing on. So the methodology, so it's in two phases, as I said. Use Whittle to come up with these ones, then build my own model when determine and compare these two algorithms. Whilst again, I have to, because of in mining, it's very we have what we call the stochastic. When we are doing mine planning, you have just one cost for load and haul. You cannot say I have this block, I can use $3.1 per ton or 2 point. You just have to give it one value. So that is the importance of doing sensitivity analysis, so that in case the load and haul cost changes, what is the impact of the net present value? People are working on building stochastic model. That is another research. But with this model, I'm using deterministic model values, and therefore you have to use like sensitivity analysis to understand these values. So these are the constraints which I told you about. You have the operational cost, selling, commodity price, your slope angle, depending on the geology of the area, you have your time cost, if there's capital cost, mining and metallurgical, you have your recovery rates, recovery factors, and there is maybe the rehabilitation cost to it. So these are the processes you go through when you are doing whittle. So when you take a block, how does it become valuable? This is actually the equation. It's just like costing. If I want to produce maybe a loaf of bread, what is the cost in producing? And after producing, how much am I going to sell it? So the same thing with the block model. How much is the gold price? What are the costs involved? So this is the general equation. So depending on the cost parameters that you have, you can just be subtracting. So this is the general, this is the basic. If it's waste, then there's no need to, add certain parameters to it. So this, for a typical mixed integer, this is what you require. First of all, you require the X, Y, Z. You require a number of blocks in it, and we have what we call the precedence. As I said, the slope. You cannot mine a block beneath, and the next year you go and mine the one above. So you still have to have how we call the precedent matrix. If you take a block here, if you want to take a block underneath, you have to take the blocks which are above it. So this formulation, I had to develop an algorithm so that I can have that using the slope angle of the pit, I can incorporate it into it. So this is the equation. As I said, it's maths. So using the value and the block. So this is my objective function. The objective function is when you are doing optimization, what is you see that you are maximizing or you are minimizing. Are you minimizing cost? Are you maximizing profit? So in this instance, in mining, we want to maximize profit. So this is the equation for it. And it's simple. It's just the value of a block. Each block, the I represents the value of each block model and the coordinates of that block. Then the slope. This is the equation for the slope. So as I said, the slope too, you have to consider the angle. So this is the equation. You come up, you do the coordinate for each block, and you come up with the blocks which have to be mined before another block can be mined. So as I said, to give you more info, this is a block, a 2D block model. So each block is labeled maybe 1, 2, 3. So to mine block 9, I have to mine block 1, 2, 3. So as I said, one of the algorithm is X to mine this. I hope you understand this. X9, if you bring X1 here, it's equal. So if any time, so when I go the model, whenever you see X9, you have to make sure you mine X1, X2, and S3. That is what this is saying. So you can write it separately in a coded when you are coding, or you can say, okay, I'll represent, because I have to mine 3 blocks here, I'll say X9 is 3. Because this equation has to be satisfied before X9 can be mined out. So these are the parameters: your metal content, your mining capacity, processing capacity, your discount factor for the MPV calculation, your grade, the time cost, the capital cost. So you come up with your objective function. This is the equation for MPV. So, and this is all that happens behind the whittle that we use. This is what is happening. And this is the decision variable. It's either mining block 1 or it's leaving it in the pit. And these are the constraints. You have the precedence, as I said. You can't mine blocks beneath before you mine the ones above. You have your reserve. You can't mine a block and you come and mine it again. Once you mine a block, it's gone. Again, mining capacity. You are limited by the time. So you see T here. If I say year 1, I want to mine 10 million, it's going to obey that. And processing capacity too is obeyed. So this is just a snapshot of some of the coding within the mathematical programming. This project probably is, as I said, try and develop your software skills. Everything is coming to it. You develop your soft skills and make sure the tools that you use for your work, you understand them. Just don't click, because there's so much involved in it. The results came up with this is for the whittle results. So the whittle gave its UP, various specials, and using the RF, that is the gold price of this one, it was even a copper mine. So using the copper price of that revenue factor, this was the ultimate pit that I selected for algorithm 1 and algorithm 2. And when you look at the difference, you can see the Whittle and algorithm 1, we achieved the same MPV. But again, as I said, the Whittle is using algorithm, which that one was solved within 8 seconds with the same model. Mine, as a start, is 15 hours. Now what I'm getting with the second phase is I've reduced it to almost around 1 hour. And the algorithm 2 was giving 1 hour. But I realized that the algorithm 2 was not giving an optimum limit. It means that I cannot use this algorithm to tackle that information. If you look at the waste and the R2, you can see the grade for the various. So this is just for the ultimate pay limit. Now when it comes to the production, you all know when it comes to Whittle just does production scheduling based on the pay shells it has generated. But the importance of the one I created was it's not limited by any pay shells. So it has the flexibility to start mining the areas that is of high value. And the result was we're almost the same. Even the Milawa balance took 4 minutes. Mine took 2 minutes. And I was having a higher MPV than the Whittle. And if you compare what I developed, you could see it's more like the balance. It's not like the Milawa, which is, you know, zigzag. So even what I did, it tries to mine the waste and opens up the pit so that you can mine the ore. So if you look at it, it's actually mining. So if you look at the year 1, it's actually targeting where there is, you know, higher ore than the others. Then the sensitivity analysis, as I did, I realized that the copper price has a very big impact on your net present value. So if the copper prices changes by 10%, it means that your MPV can change by 25%. So the same with cell recovery, processing, and the unit cost for processing. So some of the things I learned from this, which I used in the phase 2, was now I have to get rid of the algorithm 2. I have to focus on algorithm 1. Then I realized, as I said, Whittle is limited by the pay shells when it's doing production scheduling. Then I had more MPV, as I said previously, and the top 3 sensitivity analysis was on the price, your recovery, and the processing cost. So mine planning and design is a challenging problem in the mining industry, particularly when it comes to block sequencing, because even the Whittle, when it's doing UPO, doesn't consider the time value of money. It's only when it's doing production scheduling that it considers that. So if you can have a system whereby it does the UPO with the production schedule, then you can actually discount some of the blocks which are not, you know, if you don't consider the time value, will not be in the pit. Then a proper algorithm implemented can, if I didn't consider these 2 algorithms, I would have just focused on one and I wouldn't have gotten the optimum results. Then from the research can be seen there is a need for integrated, which I've spoken about. Then I realized that when you have to try and get a very good model, when you are doing the equations, don't just write them. You have to make sure the equations are efficient so that it reduces your running time. Then to achieve a good run times, the model has to be constructed in a way to reduce the number of variables and constraints whilst not compromise on the optimality of your solution. Then I've shown it to you, there's a need, this is a field that mining engineers or anyone who has interest in mine planning can take it up and also do. These are the references. Thank you.
Thank you, Ato. Go to slide 34. And the last sentence, to achieve a good run time for MILP models, the model has to be restructured in order to reduce the number of variables and constraints while not compromising on the optimality. I obviously don't want you to reduce the accuracy, so I want to put in more variables and constraints.
I was thinking of quantum computing. Yeah, because you can use the same principle, but then because our normal computing, it uses just the bits, the zeros and ones. With the quantum computing, you see, it uses quantum mechanics, which means they are superimposed. Each an entity can exist between two states, so that will speed up these processes. So then there are languages that you can use, the Q sharp, you can use to develop the model. Then it will speed up rather than maybe reducing your algorithms. You can use the same principle, but then with the quantum computing principle, you can just run everything fast. Collaborate.
To put everything in perspective, we've listened to a whole lot of very high technical, some soft, what do you call software or soft issues. When I say software, I'm not talking about computer software. I'm talking about social software. So as a young generation, you pick these issues that are coming up. And I wish you have blown my mind in mathematics here. He has blown my mind in computer. I don't understand the two of you. But if we take it serious, the two of you can produce a product that is soft on me and the industry. And that's what we should be learning and picking up from here. Thank you.
Thank you.
You made mention of the fact that when you mine, you are not going to come back to the model again. And I was a bit confused. What about cutbacks? What happened when there's a cutback?
When you are running, if it mines block 1 in year 1, it cannot mine block 1 again in year 2. That is it. So you create that equation so that it doesn't mine blocks 2 times. Yeah.